Thank you everyone to attending this webinar. Welcome to the ACG Latin American Regional Advisory Committee's technical webinar series, Geophysics for Today and Tomorrow. And today the title of the presentation is Geophysics Applied to Geothermal Projects. PowerPoint. Okay. Just a friendly reminder that this information is copyrighted. It will be available on SCG channel. So this is actually, this webinar is being recorded and it will be shared later on. So please do not record and do not copy any of the information for this presentation. The information belongs to the authors and to SCG. So we are pleasure to introduce yourself and all today our panelists. We have William Comey, Patricia De Lugao, and Luis Alonso Gallardo. Before we begin, the model of this webinar will be a short presentation delivered by our three professional panelists. There is going to be a space for questions at the end of the presentation. And if you have any questions, please use the question answer box. It could be at the bottom or at the top of your screen. I think it will be at the bottom. And due to the diversity of our panelists, if you feel more comfortable writing your question in English, Spanish, or Portuguese, you can do it, and we will help with the translation. With that said, I will pass the floor to Miguel to continue, which is our moderator for today.
Yeah, great. So welcome everybody to this panel seminar in which we are going to discuss about geophysics applied to geothermal projects. I would like to say that this seminar is organized by the Latin American Regional Committee of the SCG. We have been organizing several seminars in the line of projects regarding non-oil and gas applications of geophysics. We organized one in mining geophysics, another one in water prospection, and this one is then being in the interesting topic of geothermal. I will start presenting the different panelists that we have for today. The first one is William Comey. He's an independent consultant who provides technical services for geophysical surveys, geothermal resource assessment, geophysical research, and training in geothermal industry. He has more than 40 years in the geothermal sector, including more than 20 years in Unocal Corporation, in positions from geophysicist to chief geophysicist. Since 2000, he provided consulting services to clients in the geothermal area, academic and government industry in more than 50 geothermal fields and 200 prospects in the Americas, Southeast Asia, Europe, and Africa, so almost worldwide. His recent publications have been directed at geothermal education, geophysical research, and integrated geosciences assessment of geothermal resources. In 2013, we received a Geothermal Resource Council Special Achievement Award for outstanding contributions in improving the use of geophysical methods and conceptual models in evaluation and development of geothermal resources. He's going to give us a general vision of the geophysical methods applied to geothermal projects, geothermal area in his talk. So welcome, William, and you can start.
Okay, thank you. I'll share my screen. And I hope you see, tell me if you see a geothermal geophysics introduction slide. Is that correct, Miguel?
Yes.
Okay, so as I was introduced, I'm just going to give a general introduction to geothermal geophysics, and not just highlighting a number of methods and the kinds of things that are done in the geothermal industry, and with some reference to research. So in geothermal exploration geophysics, as opposed to also separate development, there's there's applications in at least 3 very different geothermal applications. The conventional geothermal geophysics is done in systems where you have thermal convection in natural fractures. The convection will bring the heat to within, and this will be temperatures from, let's say, about 120 Celsius to about 380 Celsius. And those temperatures will be brought to within 2 or 3 kilometers of the surface. Another general application in geophysics would be deep permeable sediments. This is where you do not have convection. It's a conductively heated system. So if you simply drill deep enough towards the center of the earth, it gets hot. And so if you have permeable sediments at those depths, you can use those for production. And that's dominated by 3D reflection seismic, whereas the conventional geothermal, the sort of method that dominates exploration would be magnetotellurics. And then another general application would be EGS fracs, and that's enhanced geothermal systems or engineered geothermal systems. They're exploring for heat much the way that a deep permeable sedimentary resource, except they would frac and create the reservoir. And in those cases, microseismic monitoring is the dominant method used just to monitor the scale of the resource. So reservoir types, there's a similar description, but ultimately the heat source is the Earth's core. We get the highest heat flow at tectonic plate boundaries. And that's where the magma would be located. But in fact, many geothermal resources are not exploring in an area where there's active magmatic, there's not volcanoes. It's where there'll be moderate heat flow in adjacent extension zones. For example, let's say in the US Basin and Range and in Antalya in Turkey. Bigger, hotter reservoirs are heated by the magma plate boundaries. So if you get the plot in the upper right shows installed megawatts are the darker colors, and the darker colors are around like the Pacific Ring of Fire in the East African Rift and in South America and Mexico. You have these smaller, moderately hot reservoirs are heated by deep circulation at faults in the extension areas, as I was saying, the Basin Range in Anatolia, but also they're in Canada, and there's a number of these newer systems in Europe, and that are also, in fact, drilled into many of them in deep sediments. So I'm going to focus most of my talk on the magma and the deep circulation heated systems. The magmatic heating systems will be 220 to 350 Celsius and range in size from about 5 to 1,000 megawatts. I've given an example here. Awi Bangkok in Indonesia is about 377 megawatts of capacity. It's got magma at uncertain depth, and I'll be discussing how easy it is and actually difficult it is to characterize magma in geothermal systems. However, from geochemistry, from the geology, you'll know that it is a magmatically heated system and from its temperature. But in fact, the focus of the geophysics will be the reservoir from about 3 kilometers depth to the surface. In a deep circulation system, the heat is derived from deep circulation in faults. You don't really talk about a heat source in this case, because in fact it's just circulation in a fault mining heat from the normal geothermal gradient in the earth. You'd like that temperature to be you'd like to be on the Ring of Fire, so it's a little shallower, but in fact you can have a system like this in Central Europe, for instance, and what matters is the focus on the system as it gets shallow enough for economic drilling. So one of the questions often is that why don't, if these systems are much larger, this is 20 megawatts for a deep circulation system, typical system versus 377. Well, the magma is localized. You have to go, it's along the Ring of Fire where you have volcanoes, whereas the thermal gradient is worldwide. You just need structures to create that deep circulation. And water is more than 120 Celsius in most places at less than 5 kilometers depth. So if you have the fracturing, you can have these deep circulation systems at less than 2 kilometers depth, because the circulation in the fractures will bring the temperatures closer to the surface. And ultimately, it's power price that matters, not the number of megawatts. We can have 30 systems like Brady's is going to be bigger than Awi Bangkok, but that does take 30 different systems. It's more costly, and the question is, what is the power price? So we always have the Earth's the core of the Earth heats the entire Earth. So you can get this kind of geothermal energy anywhere where you have structures going deep enough, or you can just economically drill deep enough to permeable sediments. So why is MT resistivity a geothermal standard? Well, in a geothermal context, at less than 10 ohmmeter zone at less than 2 kilometers is typically going to be a Smektite clay cap. And the Smektite clay cap, if you look in geothermal conceptual models, I have one here, which is a magmatically heated, distributed permeability volcanic system. And then to the right, there's a deep circulation heated focused permeability system where you have an upflow along a fault and then a distributed outflow in, in this case, a lava breccia, but this could be carbonate in, let's say, Nevada or Anatolia. And the yellow here in both these will be a equivalent of a shale cap in a oil and gas setting, but it's a clay cap that has two roles. That is, it traps heat and stores heat that we will mine with the drilling. And the other thing is it keeps cold water out. And both of those things are essential. They aren't optional to geothermal exploration. So in both these, a difference is in a volcanic system, the Smektite clay is usually created by hydrothermal alteration. In most deep circulation systems, the Smektite clay is a sedimentary shale or claystone. This is one of the earliest MT resistivity applications, and validations was that at the Salak Awi Bangkok field in Indonesia, where this cross-section was done in 1982, where we see this is a Smektite clay cap. The vertical lines here, these logs below the wells, are actually cuttings measurements of Smektite clay content done with a method called methylene blue. And this is this is a worldwide, probably the most common validation used, because running conventional well logs, wireline logs through the clay cap is a dangerous process. The clays try to have a habit of grabbing logging tools. So that the standard way of validating the MT interpretation would be to measure the Smektite clays in the wells, and then you map it out. And I include this particular slide also because this was done in 1982 using a relatively primitive 1D Bostic inversion, and it did discover a 377 megawatt field. In more modern times, essentially since about 2002, when the first 3D inversions were being applied in Chile, in fact, I think the first 3D MT application will be using a three-dimensional inversion is the standard approach. There's 2D is being more rarely used, mostly as a test of data sets. 1D is still a standard application because a 1D inversion has advantages over a 3D inversion in that the 3D inversion often has to be constrained. You'll use one kind of smoothing or another to reduce the effect of noise on the inversion. and that tends to reduce the vertical resolution. So if you're trying to match well data, or the 1D can be more effective. The problem is that the 1D, of course, has in this case, a lot of misleading distortion. So I always recommend just at a depth where you would no longer trust the data, just truncate it. This is a comparison of 1D MT Occam inversion against a 3D joint inversion at the place called Derajat in Indonesia. And it illustrates the general advantages, disadvantages. You get the top of the resource imaged reasonably well with a 1D MT inversion, but the sides of the resource at greater depth aren't represented well at all, and that's where a 3D inversion will have greater strengths. And then when you get into tweaks, like you're trying to exactly match the edges of an inversion, the joint inversion of MT gravity, in this case well data as well, was used to try to characterize the edges of that field. So we'll have the sort of one of the current standards would be to do multi-domain inversion, multi-physics inversion. So in this case, this is the Derajat reservoir again with the top of the petrophysical geothermal system shown in this mauve, and the single domain MT 3D inversion shown with the conductor shown in red. And the density inversion of gravity survey actually shows this. It's not correlated well with the reservoir and not correlated well with geology. And combining the two has the density much better correlated with the geometry of the reservoir, and the MT is fits about the same. When you do MT gravity and porosity, then we find that we can get much better detail on and a better representation of both the reservoir and the porosity of the reservoir, in this case showing density. Probably the greatest revolution, let's call it, in geothermal interpretation wasn't actually in new methods or new analyses of the data, but in combining, let's say, MT resistivity data with reservoir engineering, with petrography, and with hydrology. And this is an example where if you look at the resistivity pattern, if you correlate the resistivity pattern with the water table, with the geochemistry of a chloride spring, you see that the MT resistivity, the low resistivity, defines a clay cap that defines an outflow from a boiling reservoir here. The water outflows to the chloride spring, and the elevated, where the resistivities go above the water table, that's where you're having gas alter the rock in the vadose zone. And together, if you integrate all of these data sets together, it makes perfect sense as to what is going on in this system. Whereas looking at one data set independently of the others, you might, people did not come up with a similar interpretation. So it's the interdisciplinary integration has proven to be more effective than any of the real processing things, important though they may be. So recent developments include trying to image magma in geothermal systems, below geothermal systems, and that's been particularly important in places like East Africa, where people have imaged magma beneath the Tulmoy prospect and a number of others. The one issue here is, although I think that you can do this, and there's different data sets that support these interpretations, the interpretation and detailed assumptions that we use to interpret magma in a geothermal context has not been fully developed. It turns out that the magma develops its own cap, just from the brittle ductile zone and from silicification, and often the hot water associated with the magma doesn't end up over the magma. So having imaged a magma body doesn't tell you necessarily what you would like to know about the geothermal system. So again, we come back to integration with other lines of data. This shows in this particular case that you have both a magma image from MT 3D inversion, and this in this case is by Samrock et al. from ETH in Zurich is the 3D inversion, and then the University of Southampton has done an extensive earthquake monitoring and characterization where the lower long period seismic events have been correlated. So all these little dots are all the seismicity, and then the little gray dots, and then the color dots are various variations on the long period seismic events, which is correlated with the same magmatic feature. In a deep circulation prospect, the application of the MT is very similar in one sense. You're still looking at the clay cap, but often with a different pattern in terms of understanding how the hydrology works. You typically don't have a boiling zone and so on, and we have other complications. So in this case, we have a resistivity pattern on the left. The question would be, you've got a geothermal lead, an inactive sinter deposit, and what would this resistivity pattern tell us? And this deep resistor to the lower left, is that a not low resistivity anomaly a target? And in most managers, it turns out, find that irresistibly attractive thing to drill. And yet the fairly elaborate, in this case, series of using drilling, geochemistry, together with the geology and an intricate understanding of how the sandstone and illite alteration work in these siltstones and mudstones, allowed them to develop this resource. And this deep conductor turned out to be graphitic schist and tight. And that was a very expensive well. So interpreting the deep circulation systems, turns out requires a kind of a different set of geologic skills. But the MT resistivity part of the thing is actually quite similar. The issue is understanding the geologic setting becomes a different task. In 3D reflection seismic is used in geothermal exploration, but that's for these deep sediments. It is an absolute necessity, and MT has a rather minor role to play. In this case, we have, this is from the Malm carbonate play in Bavaria. The carbonates retain their permeability at 3.5 or 4 kilometers depth, where temperatures are quite high. It's fairly easy. It's still difficult, but relatively easy to image pinnacle reefs, but more challenging to image fractures and karsting at, in this case, 3 and 3.5 kilometer depths in the target area. You can combine reflection seismic and MT, and this is an example from Australia where you've got the red shows low resistivity shale on top of the Pretty Hill sandstone that turns out is this moderate resistivity green color. So the combination does have some role to play, but we're talking about just a few MT stations against a much larger investment in 3D seismic. And then EGS fracking is just the classic thing, is you're doing a frac job and the earthquakes tell you where your reservoir is and its geometry. So let's see, I'm kind of out of time, so I won't go into geophysics and geothermal development. If someone has questions about that, I can address that, and I'll stop sharing here.
Okay, thank you very much, William. Very interesting your presentation. We will have time to discuss. Remember, this is a web panel. We will have a kind of an hour to discuss when the 3 presentations have been already done. Now we follow with Patricia de Lugao. She's going to talk about MT methods and in general geothermal in Brazil. She received a Bachelor of Science in Environmental Engineering and Water Resources from the University of South Carolina, a master's degree in Geophysics from the Observatorio Nacional in Rio de Janeiro, and a PhD in Geophysics from the University of Utah. Patricia worked in the research department of Western Atlas, developing modeling and inversion algorithms, also in geosignal division of Western Atlas as well, working in 2- and 3-dimensional refraction tomographic techniques for static correction and initial models, and worked also in landmark with the support group supporting the interpretation of seismic data. Patricia founded in 2003 Strata Image Consultoria Ltda, foreseeing an interest in new marine electromagnetic techniques that were being developed. And from years 2003 and 2000 to 2006, Strata Image brought to Brazil companies to introduce the marine control source electromagnetic method for and seismic inversion. In 2008, Patricia participated in the first marine magnetotelluric survey offshore Brazil on the Santos Basin. She was instrumental in helping to establish the electromagnetic methods onshore and offshore in Brazil, leading most of the recent commercial onshore surveys in that country. So welcome, Patricia, and you can start your talk.
Hi, everybody. Well, I'd like to thank everybody for watching our presentation. Let me share my screen. Can you guys see my presentation?
Yeah.
Yes, we can see it.
Okay. Okay. So, well, again, thank you very much, Miguel, for the introduction, and William for the nice talk. So I'm going to talk a little bit again. I think, William, he said very well that magnetoloric, he showed that magnetoloric is the main method used in geothermal projects, although, we use other methods. So I'm going to show just some examples of Latin America and talk a little bit about Brazil. There's an introduction, and I'm going to talk about some similarities between oil and gas and geothermal targets, magnetolorics and geothermal, mostly in South America, Latin America, and Brazil, some Brazil examples, some possibilities. I like to start my talk with this page here from this book from Hans Rosling. I'm reading, I was reading this book. It's very interesting. It talks about facts, and it talks about how the world is actually much better than the media, or maybe we think, it's much better than it is. And here he has facts about like CO2 emissions and things like this. So he says that he states, which is the fact, that most of the human emitted CO2 was done in the last 50 years by countries, what he calls level 4 countries. Okay, so he doesn't divide the world in the poor countries and the rich countries. He talks about different levels that the countries, they reach different levels. And I'm talking about this because I think geothermal has can have a big impact in level 1 and level 2 countries, that we can use this type of energy to not contribute to CO2 emissions while developing the energy in these countries, okay? So I think William, he talked a lot about, different examples, but here I like this cartoon here because it shows the similarities between what he explained to be ESG and EGS, sorry, enhanced geothermal system here, where you have an injection well, and then you have a production well, and these are mostly for like low entropy, low energy systems, more shallow systems. And in the well, in the oil and gas world, we have also the same type of situation in the production. We have an injection well and we have a production well. So Bill didn't really go into the operations. Actually, I wish he had, but you know, you can see that not only from the exploration, but also from the operation, there are lots of similarities between the oil and gas businesses. So we already talked about what is geothermal energy. Is the thermal energy stored in the earth, yeah? And it's distributed between the host rock and possibly between the fluids that travel through these fractures at temperatures that are above ambient levels. So this is just a cartoon from Manzella from 2016. So this like a natural, would be like a natural system where, you know, like Bill showed, where you have volcanoes or you know, high heat flow. So you have the cold waters being heated through the faults and then coming up as hot fluid. And you see that someplace naturally, like for example in Yellowstone and places like this. Or you have the enhanced or engineered geothermal systems that I think would apply more for a country like Brazil, or like Bill said, pretty much anywhere you can have this type of system, because it just relies on the fact that you can produce hot water, but just injecting cold water. And because as you go deeper in the earth, the temperature increases. So when you reach deep enough, it will heat up this water and will bring it back as a vapor that can you know, move like a turbine or something that can be used for energy. I think Bill didn't go really so much into what is the Magnetoloric method, so I'll just have a few cartoons. So like he said, and I'm going to show some examples, is one of the most used geophysical methods for geothermal exploration. It's a frequency domain electromagnetic method, and it provides you with a resistivity model of the subsurface in that. So that's very important, because resistivity is sensitive to temperature, and the MT data is also very sensitive to lateral variations such as faults or the other geological structures that are very important when you're looking for geothermal targets. Like I said, it's a natural source method. So you have two types of sources. You have the natural solar wind at lower frequencies. At high frequencies, you have storms around the equator. These are the two sources of MT. So you have the MT data acquisition. We do some real-time data processing in the field. The process data is then sent to the office for post-processing, and we do some data editing using the coherences, for example. Then we do the different inversions. I would like to point out here what Bill said. It's also from experience that for the AMT, or the audio magnetotelluric data, which is the high frequency magnetotelluric method, let's say, usually the 1D inversion gives you really a better fit. So what he said, I agree with that from experience. You know, usually we use the 1D inversions for the shallow data, for the AMT, for the audio magnetotelluric, and the 2D or the 3D inversion for the deeper parts, because then that as you go deeper, then you're involving more stations are really contributing to that model. So the 2D, the 3D inversion will generate a more realistic model for you. So the magnetoloric method, let me just show some pictures here. It's really quick. I have this picture here of Aline, who works with us on a farm. So here we measure 3 components of the magnetic field, and 2 components of the electric field. This is on shore, and then we obtain a curve, 2 curves, apparent resistivity and phase data with frequency, along with frequency. As the frequency, this is an example of data from a sedimentary basin in Brazil, from Parecis data. So as you go from high frequency to low frequency, then you see here why, we were talking about the 1D inversion works better. You have like usually at these shallow depths, the data is more uniform. And then as you go deeper, you start finding sediments, you start finding the basement, and these two curves, they start separating, meaning there's a lot of variation. So meaning that usually at depth, the environment, the geology is more complex. And I'm going to talk a little bit about the certain part of Brazil where it's one of the areas where geothermal energy can be more applied. And this is an example of a 2D model from the south of Brazil. This goes from Uruguay all the way going northeast a little bit. And you can see the Rio Grande Arch very well. You can see the red in the sediments. I'm sorry, blue is more resistive, red is more conductive. You can see the sediments of the Paraná Basin, the Torres Syncline, which is a large feature, and the volcanics of the Serra Geral Formation, which is a large sort of basalt feature in the south of Brazil. And here's the fit of some of the stations. This is the work we did in 2012. So this shows how the method, it's really good in showing lateral variation and structure, which is something that we look for in some of the geothermal targets. Okay, so I did some research. I'm part of the Geothermal Task Force at the SG, and we did a lot of research, Latin America geothermal. And according to Bona and Coviello, 2016, what they talk about in Latin America, so I think this is an issue in Latin America mainly, is that the process of geothermal or having like a geothermal plant involves several stages, from site identification to drilling, which is expensive, construction of the plant. So this is involves a certain risk and really a large amount of capital. So, and the time, like he says, about 5 to 7 years. So, in Latin America, where sometimes things are more expensive or more difficult to obtain, then this can be an issue for geothermal energy. So we have to think about ways in Latin America to reduce the cost, and how can we make it in a way that we can reach like commercial operation in Latin America. So from also we have some information about the heat flux and the resources in different parts of South America. And Chile actually is the only so far from my research that I did that has a geothermal plant running, and you can understand why. I mean, here around there we have more volcanoes, we have more natural resource for geothermal energy along the Andes region. Well, I have to talk about the work of Professor Ethel Morales. She's a professor at the University in Uruguay. And she just has recently a paper on the potential of geothermal energy in the onshore sedimentary basins of Uruguay. So this is very interesting. She did this work using magnetolorics. Actually, we are currently in Uruguay finishing a survey there. And so here she used MT to map the sediments, the volcanic rocks, the conductive sediments between the faults that can be used as a source, as a place for enhanced geothermal system. And I'm going to talk a little bit about Brazil now. Brazil specifically has enthalpy values, so it's like a low, what they call low enthalpy area, between 80 and 100 megawatts per square meter. It's very close. It's pretty much like continental country, so these values are small. there are some areas in Brazil that, you know, that have higher temperatures. For example, the state of Goiás, I'm going to show work that I did many years ago. In Santa Catarina, now some work that may develop. Okay, so in Goiás, the thermal waters are mostly used for recreation, so it's not really used for energy or anything like that. Although it could, you know, we have to think how can we do that. This cartoon is not very nice because it's a paper, but this is the geothermal map from Brazil. You can see here there are some higher areas here of geothermal resources, also in the Amazon. This is also the work of Professor Hamza from Observatório Nacional in Brazil. And here is a cartoon with the Paraná Basin. And in blue, the basalt cover in the area that may contribute to some geothermal resources there too. Caldas Novas, like I said, I'm going to show this is work we did, you know, very limited. I'd like to maybe go again to that area, get more stations, and we do this work. It was located in this Caldas Novas, which is an important geothermal area and tourist attraction in the state of Goiás, pretty much in the center of Brazil. The Observatório Nacional acquired like 26 stations along two profiles just over the Caldas area. And we obtained like a very simple model, which the inversion at the time was very limited, the data that we had, but just showing mainly some structure, you know, the basing and some structure of the area that, and some more resistive structure that related to some quartzite in the area and structure. Okay, I know this is a lot of text, but this was taken from the beginning of a geothermal generation project in Brazil. So what happened was this company, along with the University of Paraná, the Federal University of Paraná, they researched several areas in Brazil that had better thermal gradients. And they found two places in Brazil, two smaller areas in a region called Charqueadas in Rio Grande do Sul, and the other one called Capivari Baixo in Santa Catarina. The one on the south, I'm going to show the map. And then we were called because you know, as the people in this company, they knew they understood that Magnetoloric had a long history in geothermal exploration. So they thought, okay, we can use 2D modeling or even three-dimensional imaging in geothermal prospecting for these reservoirs, and they located these two areas, which are here in this map. So this is a map from a paper from Gomez. It's from 2018. That talks about like the energy, the possible energy. And these are the two areas. You can see that they have higher energy potential. This is the Capivari de Baixo in Santa Catarina, and the other one in Charqueadas. And right here, it's the contour of the Paraná Basin, this whole thing here. So you can tell, you can see that not only they are in this area where you have probably you have the basalt, but also you have the faulting system there that may help in the use of the geothermal system. So the conclusion is that the need to decrease the use of fossil fuels can be addressed by geophysics and by the tools that we already have from the oil and gas business, because geothermal is one of the closest to oil and gas exploration. And of all the methods that are used for oil and gas, MT has already been used extensively for geothermal exploration. But like, you know, William showed, you need also well log information, then you need the drilling, gravity and magnetics and also can be used. So I'm gonna stop sharing now. Okay, thank you.
Okay, thank you very much, Patricia, for your very interesting presentation. We are going to have next our third panelist with Alonso Gallardo. He's going to talk us about the geophysical methods applied to geothermal in Mexico and perspectives of the sector in Mexico as well. Luis Alonso is titular researcher in the Department of Applied Geophysics and the current head director of the Earth Science Division at the CICESE, Mexico. Since 2005, he has been national scientist from the National Council of Science and Technology in Mexico. He obtained his PhD in environmental sciences from Lancaster University, United Kingdom, and held GUVD lectureship at the University of Western Australia from 2009, between 2009 and 2011. He was nominated as Outstanding Reviewer in the journal Geophysics in the year 2011, also awarded as prestigious SEG Reginald Fissenden Award in 2019 for the development of the cross-gradient joint inversion approach. And also the Luis Anda and Barrera Medal 2020 as a fellow distinguished graduate of the Instituto Politécnico Nacional of Mexico. The research of Luis focuses on geophysical inverse theory and joint inversion of gravity, electromagnetic, and seismic data. He worked on multiple projects from geothermal exploration funded by private companies and government agencies in Mexico. He has also worked on geophysical imaging for mineral and petroleum exploration in Western Australia, Western Turkey, Brazil, East.
Okay, sorry, I think I missed.
Miguel, are you there?
Yes, did you, just to clarify, did you listen my introduction completely? Because I'm in Europe and the network is saying it's a bit unstable, but I'm not sure if it reached everybody complete.
Almost completely, I think.
All right.
So it's fine.
Right.
Thanks, Miguel. So, I will start my talk sharing this screen and okay. So my talk will detail about some of my own experience in the characterization of geothermal fields in Mexico. And it's basically based on the applications on two specific areas, which are two caldera scenarios in the center of Mexico, the Acapulco caldera. And before that, I will start with a brief introduction about geothermal fields in Mexico and joint inversion. Mexico, it's a country that is surrounded by several tectonic plates. And of course, it is thanks to all this movement between the plates, we have several areas which are very attractive in terms of geothermal energy. So we have the most larger rates of heat flow in the country belong to actually transport zones of the tectonic plates, which include San Andreas Fault and the Gulf of California, the Mexican volcanic belt at the center of Mexico, and the southern volcanoes, which are related to the contact between the Caribbean, Pacific, and Cocos Plate. So we have those three areas with the largest heat flow. And in Mexico, we have several fields already developed. We have 4 of them, which are run actually by the Commission of Electricity in Mexico. The largest one, Cerro Prieto, and we have 3 smaller ones. And we have one field developed by a private company in Domos, San Pedro. That's in Nayarit, near to La Primavera. From this, we'll talk about 2 specific areas, which are Acapulco and Los Humeros. Both of them are in the Transmexican volcanic belt. Okay, when we talk about geothermal exploration in geophysics, if I search papers referring to these topics, so we see that an increasing report of geophysical studies for geothermal. My work is related with two large projects in Mexico, which are part of the government initiatives to promote clean energies in the country. It's SEMI-GEO 2014 and HEMEX 2016. Those projects provided most of the data and analysis that I'm going to show in this talk. This image you already saw, and what I have at the left, it's a statement from one paper, and I brought it here because it calls the popular use of geophysics for geothermal targets. For instance, we say in the first paragraph that all the methods have some advantages and disadvantages. That is something that I found a tiny bit unfortunate in terms that methods are not advantageous. That means it's not a competition. It's just the capacities that each one of the methods can provide to detect or not a target. And then it divides the methods into direct methods, which are said to target directly geothermal activity. Among those direct methods, we can talk about geophysical well logs, self-potential, and geoelectrical methods. And then divides the second lot in structural methods or indirect methods, which belong to seismics, gravity, magnetics, and they are mostly related to define the structure and the overall understanding of the geothermal system. So in general, when we talk about magnetotellurics, we try to identify specific features, mostly clay cap, reservoir fluid, reservoir structure, heat source, and of course it can provide, or it provides the structural information for the geothermal areas. Gravity is mainly focused to study basement interactions, which are the largest contrast for density, and magnetics usually focuses on basement and heat sources, and they are used less than the other 2 methods. So some questions that I would like to bring forward here is from this division of methods between structural or indirect methods and direct methods, we have several specific questions. For instance, for structural methods, we would like to see whether they can become, instead of structural methods, they can be direct methods. That means they can be useful to actual reservoir characterization, whether the properties that this method sends are actually influenced directly by geothermal activity, and whether they can be detected. And for the direct methods, of course, is that we still have plenty of challenges, like distinguishing whether we're seeing clay cap or we are seeing the fluid composition that affects, for instance, the conductivity. And how can multiple geophysical data can help to reveal rock, fluid, and temperature interactions, which are complicated, all of them together in the geothermal systems. And whether these interactions or signatures are replicated in geothermal environments. So what is the features that we expect in joint inversion for geothermal? Okay, there are several frameworks for joint inversion. This is an image of a specific target. They will say this, the perspective of one of the characteristics of the target. And of course, the target can be described using several characteristics of several parameters. parameter M1, for instance, resistivity, parameter M2, for instance, density. And because they belong to the same picture, they should be enclosed by the same structure. They belong to the same volume. And of course, if we can characterize the structure of this feature, then we say we have a specific aspect of the target that we can describe. Then if we go and analyze each combined value of these two properties for each specific element or substance that we have at every position and map in terms of the properties, then we have a characterization of the actual values that help us to define each one of the substances that compose the target. And what we'll see in this talk is that, of course, we have several parameters, and the objective in an integrated interpretation is to actually interpret all the parameters together. So the strategy that I like to use here is something that I call Spectral Image, which means we try to connect each one of the parameters to specific sensors that we have in our body, and our brain will do the rest. That means it integrates and provides a fused or composed interpretation of the target. In this case, I use 2 bands of the electromagnetic spectrum, in this case, red and green, which is connected to our visual skills to produce a full color image. In this case, the image at the bottom. And each one of the combined values of the properties will be assigned automatically by our brain and a specific feature that we call color. So this is just spectral image, and what you will see in all the experiments or the images from the rest of the talk will be practically these images. Joint inversion, in general, tries to combine these parameters and produce the better integrated image of the subsurface possible. The idea of joint inversion algorithms is to find geophysical models, M1 and M2, for instance, that fit the data, and trying to make these geophysical models to comply with one specific linking characteristic. In my case, I will use the structure given by this equation below. This is an example of a volcanic area. It's a 17-kilometer profile for gravity and magnetic data. And what we have here is a separate inversion of both data sets. So we have the distribution of density in the area, which is given by these contours of density, but we also have the distribution of the magnetic properties given by these other contours. In any conventional independent inversion of both geophysical data, we will have an incoherent structure. If we apply the joint inversion, assuming that this structural framework is common, we can find, of course, a density distribution and a magnetization distribution that produces an integrated geospectral image that is more focused. The things that we can interpret from these images are, for instance, if I combine density and magnetization as I was describing in a red and green image, we can detect this band of colors. And the key feature here is that each one of these properties has a predominant influence by one of the features of the rocks. In this case, magnetization is mainly driven by mineralogy, and density is mostly driven by compaction. Of course, there are other features, like density is also influenced by composition and so forth. But the most remarkable features that influence the variations in these properties are these two. And using these features, we can start distinguishing whether one rock is low magnetic and low density, like sediments, and whether one rock is very dense and very magnetic, like the features given by ultramafic rocks at the upper corner. So we add in this term an additional feature, which is the electrical conductivity, for instance. Electrical conductivity is in the Earth is due, in most of the cases, to the fluid content, in particular water. Whether the water is very saline, it's really saline or not, it only influences a higher or lower conductivity. But in general, conductivity is driven by water. So if we have the same materials and they become conductive, we can use the blue color to use our third sensor in our eyes and provide a full red, green, and blue image. In this case, this material will look black when it is dry, but it will look blue when it is wet. And so for each one of the interpretation or the colors that we originally assigned based on the compaction and mineralogy, it's also, or it can be also added, the humidity. In this case, this is a profile in Los Humeros, central of Mexico. And in here we have the fusion of the three properties: density, magnetization, and electrical conductivity. And indeed, we can distinguish a specific basement, which is very dense, non-magnetic, and non-conductive, which is the green one at the bottom. And we can see several conductors on top. So we can actually interpret conventional MT, for instance, magnetization from magnetics, and density from gravity in a single image. So what we'll see in these two examples are these in practice in two perspective areas in Mexico. Here we have the Acapulco area. The Acapulco area is a caldera. It's about 15 kilometers diameter caldera. And the area was prospected in 30 years ago using geophysical and geological mapping. And Comisión Federal de Electricidad drilled one well in the area, 2-kilometer well, and they detected high temperatures at 2 kilometers, and they crossed several units: granites, then 800 meters of skarn, and then 800 meters of volcanic deposits. So the image at the right is the first conceptual model for the area in 2009. And it describes a limestone basement, which is intruded by 2 episodes of magmatic events. The second one is the one that is deemed to cause the geothermal activity for the area, while the first one produces the caldera structure. For this area, we have a 20 times 22 kilometer survey area. And for this, I am using originally gravity and magnetic data. And these are collected originally for geothermal exploration. And with this data, we can produce this 3D model. This is a geospectral volume. It is the same color scale that I presented to you before, but it's in practice, meaning that each one of these 200 times 200 meter cubes has a specific combination of properties of density and magnetization, which will enable us to distinguish the different units in a volumetric context. So this is the volume, and what we'll see here is that we can start characterizing these features in terms of unit A, which will be the less dense material, unit B, the high density material, and several specific units in between, whether they are magnetic or not, given a set of basement configuration with several units and a volcanic cover. So the representation of these units will be, this is the basement in the area, these 2 blocks at the area are the actual wells drilled. And we have a basement composed by 4 different units. This is the main caldera in the center, which is this orange area, and the deepest area of the caldera to the northeast of the area. The basement is composed by a non-magnetic intrusive. One of them is crossed by these wells, and the other one is on the right, on the northwest of the area. We have the second set of intrusions, which are magnetic, and they are practically the ones that are responsible of the later geothermal activity for the area. And we have the altered zone, which are the skarn that corresponds to the limestone basement, which is altered by these new intrusions in the area. This is, of course, covered by sediments on top. To analyze this in more detail, we have this 2D section, and we have gravity, magnetics, and in this case, we have DC resistivity soundings. So we have the inversion for the 3 data sets, and this is the gravity and magnetic geospectral image, which is density and magnetization. We can see the features and the well at the center. And this is the area covered by electrical soundings using large AB/2 spreads of 4 kilometers, which give us a nominal depth of penetration of about 1.5 kilometers. So what we see here is that in this effect, whether the rock will change the color. If it is wet, and it will become bluish. So what we can see here is that the center of the area is completely dry, and therefore that confirms that the well in the area was not very permeable. And at that time, at the original time, this area was abandoned, but it's not studied again in terms of becoming an enhanced geothermal systems. We're targeting this dry, hot material at the bottom, which is the underlying intrusion. This, of course, matches the resurgent caldera in the area, and it matches, of course, the surface geology. For this area, we can see that we can distinguish the several intrusives, and we can interpret the area in terms of the potential of becoming an enhanced geothermal system. And if we start stimulating this area around the well, what we'll see is that the main structures are oriented in that direction, and it also goes in line with the direction of the slope of the basement, which means that it is very likely that the fractures will develop in this specific direction, which is actually that has been something that is being measured by the seismic activity at the moment. The second example is Los Sumeros, which is also a caldera field. And this is composed by a large ring, about also 15 kilometers diameter, and it has several inner structures in it. It is also a limestone basement overlain by volcanic deposits. In this case, this field has been in production several decades ago, and it has 60 wells. The temperature of the in the wells reaches about 300 degrees Celsius, and we are currently exploring his potential as a super hot geothermal system. So for this, we have empty data at the center of the area. These dots in the middle are the actual wells. The characteristic in this area is that some of these wells are productive, some of them are not productive, and they are very close one to another. So it is very intriguing how is the control of the reservoir at depth. Most of them reach depths about 2 kilometers and more. The square, the white square in the area corresponds to the volume that I will be showing later, and the 2 lines correspond to 2 specific sections. So for this area, we also have gravity and magnetic data. So this model is constructed with the joint inversion of gravity and magnetics as constrained by a 3D MT model of the area. So what we see here is that we can actually interpret not only the composition of the materials and their level of compaction given by the density and magnetization, but also we can determine whether they might be wet or not. In this case, the different units are divided, as you can see in the scale below, depending whether they are dry or wet. Of course, meaning that they are wet doesn't mean that they permit the circulation of the fluids. It only means that they have the fluids already contained. So the basement in the area is given by these for these two B units, B0 and B1, and it shows the main structure of the caldera. And of course, at the margins of this structure is where we have all this geothermal field. The first volcanic deposit, the deepest one, is in the margins of the caldera, and it corresponds exactly in the position of the geothermal field, and where we have the 60 wells, but it of course surrounds the whole caldera. We have this covered or capped by two episodes or several episodes of volcanism, which is more magnetic, and we have a later deposit of andesites on top, which are very magnetic and are providing the seal for the geothermal system. So to see the behavior of this area at depth, we have these two sections. And in these sections, we have the actual 2D joint inversion of gravity, magnetics, and MT data. What we can see here is this couple of full color images where we can distinguish the basement, we can distinguish the lower conductor that corresponds to the deepest volcanic unit, which is providing the transit of the fluids at depth, and the cap on top by the other set of volcanic deposits, which are different in composition, accommodation, and of course, conductivity. The actual geothermal field, this is a section about 4 kilometers depth. And we have the wells on this area, which are the productive area. The deepest portion of the caldera is this circle. And the main unit that we are seeing at this area is actually the same unit that we see rising where we have these wells. So what we expect here is that if the heat reaches this area, it may also reach some other areas. And of course, the proposal here is that we should start exploring not only the area around the geothermal field that is already known, but also the one that has similar behavior. In this case, this second area, which behaves very similar to the actual area that is exploited at the moment. So the importance of all this geophysical information for an enhanced geothermal system like it will be developed in Acapulco and a super hot geothermal system depends, of course, on several features like fluid connectivity. And of course, this fluid connectivity depends very much, it's very important for an EGS because it determines the feasibility of the reservoir. And of course, the second aspect that we have to look after is the chemical interactions that may seal the connectivity that is developed in the system. Of course, we have to check whether we have uncontrolled connectivity to other water reservoirs. For super hot geothermal systems, we have to be very careful on the control at depth of the reservoir and the chemical interactions. And for these two specific areas, of course, we are seeing that this joint inversion reconciles several features, which include the fluid content, the rock composition, and the geological structure, provides knowledge of reservoir connections, can assess the rock fluid associations at depth, of course, far beyond the reach of these exploration wells. And it provides the required structure for future reservoir simulators, which is the last part during the exploitation process of the reservoir. With this, I say thanks to all of you and will conclude my presentation. Thank you.
Well, thank you very much. Thank you very much, Luis, for your presentation. Interesting combination of different type of geophysical data, magnetic, gravity, and electric, either MT or TC, for in a joint inversion guided by a structure. So, well, we can start now our next phase of this meeting, which is to discuss. We want to discuss on the geothermal techniques, geophysics, the perspectives of the geothermal applications in Latin America and all Americas. And I will try to go through the questions that has been already written to organize some of this. I've seen that there are about three, 4 questions would need to obtain or to upgrade, say, to update in order to move towards the geothermal area. So either in the terms of methods or in the terms of geology of the geothermal systems, etc. I would like all you 3 panelists, if you can briefly comment on this. Whoever wants to start, Patricia, go ahead.
I can start. Well, I think I showed in the first slides what are the similarities between oil and gas and geothermal exploration. And William and Luis, I mean, I think they showed that all methods apply to geothermal. So, you know, of course, magnetoloric has been most used, but for magnetic methods, I would say. But you know, he showed examples of seismic, gravity, magnetics is very important also. So I think any experience that you have well logging and then in drilling. So it seems to me, you know, like I said also in the first slide, that all the experiences in and methods in oil and gas can be applied to geothermal. So there's not like one specific area, you know. I think that can be moved straight. I don't know what Luis and William.
Mm-hmm.
Luis?
Definitely agree, yes. One of the aspects that I see when I talk about these geothermal prospects is that all the complicated features that you may think may happen, they actually happen in those areas. I mean, you have the complexity of the structure. That means if you want to have some heat, of course, you need to have something that generates the heat. And generally that becomes because of the movement of the rocks at the bottom. And that means you expect to have volcanic expressions on the surface, which are already complicated for geophysics. You need to follow these expressions at depth, which is actually the continuation of this, what you see on the surface. And you have all the known interactions, as Patricia was saying, that we have in oil exploration. So we actually have to look after the connecting paths and everything, which is already a complicated subject. So my key expectation always is that prepared to face the most complicated challenges for geophysics. So that is, you have to be very open and you have to be able to handle as many tools as you can have for all the geophysical methods. Very, very interesting topics always.
Would you like to comment, Bill? Yes.
Sure. It's a question I get asked a lot with the complications in the oil and gas business, and if you're not in the gold business, the complications in mining also. Geothermal. I've got. So I guess one thing to just emblematic. Reykjavik University had 9 graduate students in geothermal year before last. This year they have 53 applicants in the master's and PhD programs. And that's because people are looking for a transition. I'd like to also point out this, I'm going to be I'll be the hard truth person here then. I'm not trying to discourage you because obviously people get attracted to the geothermal business, partly because, the reason I ended up in geothermal was partly because, greeny things and so on from 50 years ago. But also I didn't like doing one thing. And if you're in the oil and gas business, basically, when I was looking at that, it would have been strictly reflection seismic. And really, when they said geophysics, and actually, if you're in the geothermal business and you work for an oil and gas company doing geothermal, they'll say, "Why don't you do geophysics?" Actually, they mean, "Why don't you do reflection seismic?" Let's say on a volcano. And there's lots of reasons why that wouldn't be so. And then you say, well, we do use reflection seismic if that looks like it's going to be an appropriate technique. But the issue is we use lots of techniques. MT has many advantages, but actually I don't know, some 10% of the reports I've written over the years have been why somebody shouldn't do MT on a particular project. It's not something magic that you just do everywhere. So South Australia, I showed an example of MT in South Australia. I thought they could have done 20 MT stations and got the goodness out of that. They did 180. I thought that was probably not a wise investment. The reflection seismic had a much higher value in that case. But actually, you were saying how would you make that transition? Well, learn something, read some papers, learn something about the geothermal industry, learn something about its current status in the countries where you're likely to be able to work. And this is an issue. If you can join an international consultancy, it matters a little less where you work everywhere. However, if you're going to be working in a particular country, you need to know the status of the industry in that country. So for many years, for example, Peru did not have a geothermal law. Joining a geothermal company in Peru would be a high-risk endeavor when they didn't have a law to govern the resource. Mexico, the geothermal business is very cyclic, just like the oil and gas business. They say, well, why would oil and gas affect geothermal? Well, the issue is power prices are what drives the geothermal industry in the end. And you have governments contributing and so on. But when energy prices are low, power prices are low, and that hurts geothermal developers. And so right now, most of the world's drilling is going on in Indonesia and East Africa. And there is one geothermal field running outside of Mexico. That's in Chile, but that's Chile had an active exploration program now since since the late 70s, and it has one geothermal field. So it has taken a long time, and people say, why? Well, we had proposed a geothermal power plant in Chile in 1997, a place called La Torta, and another company bid a gas plant for 2 cents a kilowatt, and our price, the lowest price geothermal power plant could then offer was 5 cents, 2.5 times that. And so if somebody's going to offer a gas plant competitive with geothermal, then you need some other angle, like you will get carbon credits or something else. So these are just practical issues. If you want to join the geothermal industry, you can go on to the Geothermal Rising, the International Geothermal Association. Most of this is in English, but there's a lot of Spanish, not a lot of Portuguese language discussion, but Patricia could probably clarify that to tell you what is going on in the industry, and then learn something about it. But just to be straightforward, I gave that example of Reykjavik University. This is common throughout the world right now. Almost every university geothermal program has expanded its student engagement by a factor of 2 or 3 or 4. So this is the University of Nevada, Reno, the University of Indonesia, the University of Auckland. All these programs have had a huge influx of interest because of well, wanting to get out of oil and gas mostly. But so that's a heads up. Is that the other thing is it's a much smaller industry than oil and gas. So if everybody in oil and gas tried to go into geothermal, we did an inventory. There were something like 200 active geophysicists working on actual industry applications, not doing like other than research, worldwide in the geothermal business, against something on the order of 12,000 in oil and gas. So you can't just say that all those oil and gas people can make a transition to the geothermal industry, the demand, even if we doubled the number of geophysicists. Having said that, 5 geophysicists were hired in the United States last year. It was shocking in the geothermal business. So it does happen. But, you know, I'm sort of being hard truths here. In terms of skills, I would say people who want to do just their thing, the geothermal business isn't really a good fit. So we just said that MT is kind of the soul of the much of geothermal exploration. And I've spent maybe a third of my career doing MT. I've spent a bunch of it on reflection seismic gravity, magnet. I mean, people think I'm often a geochemist because I've written a number of papers on geochemistry. And I'd say that the thing that every geoscientist needs to know is the thermodynamics of geothermal systems and how that works. So reservoir engineering, essentially. Well, if that sort of description appeals to you of doing everything, well, when you interview with a company, one of the larger companies worldwide or a consultancy, what they are looking for is somebody who would say, not that I'm a seismologist and I want to do S-wave inversion, or I'm a MT expert and I want to work on phase decomposition. Well, that kind of almost disqualifies you because this is a research topic. This isn't an application. If somebody comes in and says, I'd like to know, I'm an MT expert and I want to know something about clay diagenesis. Well, that's interesting. And if you say that you want to know, how the structure plays out with respect to alteration and geophysical data sets, those are the kinds of issues that will be attractive. In other words, somebody who wants to look at the whole problem. And so that would be really, I'm saying is that if that doesn't really appeal to you, then it's kind of getting into the business will be uncomfortable for you. Because if you join a geothermal company and like one of the larger ones like Ormat, I know a geophysicist who's over there and he's sitting a well right now and describing cuttings. It's and if that doesn't seem like what you want to do, well, that's kind of the nature of the job is and also actually in the company I worked for, Unical, about 2/3 of the geophysicists that joined Unical eventually became reservoir engineers. And so you were basically people, if you're the definition of a geophysicist is you do what comes up.
Well, can I just say something though? I mean, I understand what you're saying, about the fact that you have few people working in geothermal and this large number working in oil and gas, and that these people are not going to move, if all these people move to geothermal. But, don't you think maybe that geothermal is much broader? I'm sorry, I'm getting to the question here. This started discussion, maybe for the other ones to think. Oil and gas it's very punctual. Like you work in only specific places in the world. There are only few places where you can work in the world with oil and gas. While with geothermal, I mean, it's much broader, and in a way, although, for example, you have been working with geothermal for many years, it's like a starting industry. Like Latin America, like you said, like also I surveyed, there's one plant in Chile when there could be many more. I understand the energy price, but also, the other thing, there's now the carbon market, you know, like in Brazil right now, we have a problem that we have an energy problem in Brazil, and what's going on in the country, and yes, but what's happening now is that we are putting in action all these thermal plants, all these gas plants. When we have maybe not so much geothermal, maybe like maybe like low energy projects, yes, we could have, but we could have tons of solar, wind, and we are putting a lot of effort in the thermal plants, in the gas plants. So I think, yes, I understand there are only a few people working. Maybe not everybody in the oil and gas gonna move, but I see the geothermal market as a starting market that will be pushed more. We push more to these markets because of the like what I said in my first slide, because of the CO2 emissions. We have to lower this. I mean, there are targets. There are targets.
I guess I didn't mean to, obviously, since I spent 40 years in the geothermal business, I didn't mean to slam it as being what I was saying, though, is that because the change in employment level in the oil and gas business has been dramatic, thousands, that the rate of uptake in the geothermal business, in geophysics, I don't think, I mean, what I'm saying is not that it's not an interesting topic and not that I think that it is going to be a growing industry. It's that people should consider if the qualities of are you interested in, if somebody is interested, is a reflection seismic expert and wants to stay in that narrow domain, then there are a couple of possibilities. If you're in the Netherlands, there are places, if you're in the Malm play in Germany. But the thing is, right now, that is a well-populated area. Now, there's a lot of people in that already. And so it's a very competitive environment. But again, there are these opportunities to in the geothermal realm, as you pointed out. I think that it will continue to have opportunities. The issue is, I'm not sure about like the ratio of 12,000 to a few hundred is the industry can't bear that influx. It's not going to absorb that change. And so people should consider this carefully rather than be naive that that geothermal will have a boom in geothermal would be 200 new geophysicists. That would be a boom. And, there's literally thousands of unemployed geophysicists in the oil and gas sector.
Yeah, I very much agree with all the comments, of course. And I think that everything depends on the size of the industry. I mean, petroleum industry has a very large size and it gives room for many specialized works for any geophysicist. So there are too many people working for the industry that you can easily specialize in one specific area. Whilst in geothermal, it is mostly like we have to deal with most of the activity. But it's also, of course, if we, as you were saying, if we populate the world with geophysicists or people working for geothermal industry, probably at the end it won't provide enough room for everyone to fit. I mean, in Mexico, we have this boom in geophysics and geology for geothermal, and it became in 2014 with all the initiatives from the government. And we changed from having only a few geologists devoted to geothermal exploration, to have plenty of them in the country. So it is pushing the industry a tiny bit higher in the country, but of course it's not the size of the petroleum industry. But still, people that is going into geothermal that has these capabilities easily translate back into petroleum or other industries. So they have plenty of skills and they adapt very easily to the other applications of geophysics, really.
I might point out something here, and actually, some of the more successful people. All the thing that I was. There's a couple of questions about Smektite clays, and now that is that is a very complicated story, because it turns out zeolites are another aspect of this. The alteration of rocks and the alteration of sedimentary rocks and shales is a complicated subject all its own. But it turns out, fracking isn't a very popular thing, but the process of fracking shales is very much related to the coherence of clay caps in geothermal systems. The reason, if you have a high Smektite content in shales, you can't frack it, just in the same sense that makes a coherent cap, even if it's faulted in a geothermal context. Well, it turns out if you although fracking is a very controversial issue, making that environmentally effective is probably going to depend on very similar petrophysical issues to what we deal with as sort of the default condition in the geothermal business. So things like, so I have a paper that I wrote in 2000 on the measurement of Smektite clays. And I was surprised to discover, it is one of my most popular papers, and almost everybody who's using it is from oil and gas in the fracking business, and which wasn't the intention, but we were just talking about measuring Smektite in cuttings, and that is a big deal. And so some of these tools do translate back in unexpected ways. This was completely was a surprise to me, and but it's not necessarily a direct thing. I don't know what will necessarily translate back and forth. Certainly, if you're in deep sedimentary geothermal systems, like they're developing in Canada, in the Netherlands, in Germany, the skill sets are identical, really, to oil and gas, and they're harder. You're dealing with deep fractured and deep karsted geothermal systems, and these are among the most difficult targets in the oil and gas business. So, there would be, if that is a possibility for, if you're in a country that has those kinds of deep sedimentary targets, that would be finding a company that's looking at that and looking for expertise in that, and you have that expertise, there's something you can transition back and forth, and your expertise would be directly translatable.
Yes, I would like to comment that the discussion on the contents, on technologies that are used in geothermal projects is relevant, because SEG may promote some courses, for instance, to complement. Bill told us about the universities that are getting larger amount of students on the geothermal programs. But concerning current geophysicists working in the oil and gas sector, then the societies may promote some courses. I would say that electromagnetic methods.
I guess Miguel's lost his connection. Luis, how many, are you familiar with how many students are moving between? Oh, okay, you're back.
Yeah, right. So electromagnetic methods could be one of these areas to generate courses, or the geology of the geothermal systems, that is quite different from the oil and gas, could be another one. And let's figure out. It's interesting, and it is in one of the questions as well that one of the participants made.
I was going to ask Luis and Patricia, there is historically, for example, the SEG, it's mining and geothermal. The geothermal issues were always classed with the mining because of the use of electrical methods and potential fields and so on in the previous less, the more narrower applications of reflection seismic. In Mexico and Brazil, well, particularly Mexico, there's a big, for example, precious metals mining business and so on. Are you familiar with how much move back and forth there is between geothermal and mining?
Yes, in Mexico, mining industry, geophysics within mining industry is not as developed as it is now in geothermal. So I would say that it's more normal now that people that is working in mining exploration, geophysics moves to other fields. Mining companies are very restricted to mostly private companies and the high sierras in Mexico, and the analogies are not as good as I would expect. Mining is hydrothermal in Mexico, most of them, and it is a hydrothermal system which already lost the dynamism. So it is a fossil hydrothermal system, most of them. So the features that you may have learned from mining, you can apply them in geothermal. But it's not the same because, of course, you have to go into the dynamic part given by the fluids. But really, there is not much interaction. And that will say at the moment, geothermal exploration is a tiny bit higher than mineral exploration, at least in Mexico. So if I put them in a scale, I would say, of course, petroleum industry, and then comes now in terms of earth scientists, then we may go into water, then geothermal, and at the end we go into mining. So geothermal is pushing very hard, but hopefully we will have this reflecting in more geothermal fields in the very near future. But it's not that comparable in mining and geothermal, at least in Mexico. It's for geophysicists.
So I know that, go ahead.
Okay, well, because you were asking, actually in Brazil, so far, I can tell that there's almost no effort for geothermal. And of course, you're talking about mining is something else, but even mining, geophysics is very limited in mining in Brazil also. Just to the, what can I say, to the classical gravity, magnetics, very little MT done. Most the EM is mostly like time domain, things like this. Geothermal, there's a question here. What would take to countries with low geothermal gradients in Brazil to consider geothermal as a source of energy? Can EGS be a possible alternative? Yes, of course. It would just take the fact that what William was talking about, if we could make the energy from geothermal competitive. So we need to think, what exploration methods can we use that are not so expensive? What also like the drilling, maybe we can look these EGS systems. I think William and Luis can.
Okay, I would like to make you another question.
Yeah, they're like.
Oh, sorry if I.
They are more like shallow targets. These low enthalpy targets, they're shallower targets, right, Will? So that would be more possible for low thermal gradient countries like Brazil, for example.
Okay. Yes, in the perspective of the current pressure that the industry has in reducing CO2 emissions, how do you see the geothermal activity as a competitor to solar and wind, for instance? Do you see geothermal has a great potential in this future competition? We are talking a long term, 20 years, something like that. Would you please give your view on that?
Well, I know right now, I get involved in due diligence studies in around the world. I have not looked at solar versus geothermal in Latin America within the last 5 years, but I have looked at that issue in Africa. And the issue is because it's base load, geothermal, that is, it runs all the time. So if the key thing would be if battery storage, for example, will reach, and I'm not going to get into exact numbers here, but there will be a trigger point at which when battery storage would get, the price gets low enough that it would be hard to see how geothermal would compete. The thing is that that price point looks like it's going to be a ways away. So, and when I say a ways away, some people would say never. I think that's too strong a claim, but certainly the thing is that to some extent, high temperature geothermal is a niche thing. In many situations, for example, in Kenya, geothermal power prices will beat anything else because they have high temperature resources. Or New Zealand, the geothermal projects in New Zealand are bid out at competitive market rates. There's no benefits, there's no carbon credits. It's just straight up bid into the market. And so you can win power prices. It was harder to do in Chile because they were getting very low gas price bids. And, as you run out of gas, then that goes away. Then the question is, what about solar power? Well, you see, this is hard to predict because what's the price of lithium going to be in 15 years? And things like that's what it depends on. So it becomes in the end, although it's solar and all that, because you have to somehow average that out through the day, it becomes one of, you have some resource like lithium that will be the controlling. What is the price of lithium is going to be whether we're competitive in geothermal. And, what's your magic ball on that?
Well, Bill, you're talking about lithium if you talk about batteries, right?
I'm speaking of to make the big threat to, would you say, geothermal, offsetting geothermal would be solar.
Yeah.
Well, the thing is, the solar power itself, even right now, it becomes, you can get, it's kind of for low and moderate temperature high temperature resources can still compete against solar just fine. Lower temperature resources, it becomes more difficult, except that they can't provide base load. Well, if they can, then it becomes an issue of storage. Like if they can put in a lithium battery array and run the solar power essentially 24 hours a day, then we can't beat that. But that is an expensive option now. So but the question would be, when will lithium battery storage be so low priced that we can't compete with it? And the way people look at that tends to be like they assume that the price of lithium as the whole world adjusts to solar doesn't change. And this isn't the way the world will work. So, but the question, my issue would be, this is a complicated question and smart people disagree about it. So, but it is obviously, when you're evaluating geothermal in a particular location, in the Aleutian Islands, they have, for example, some geothermal options that are very expensive. Well, their option is diesel, and solar is not going to work. It's dark 2/3 of the year up there. They can't use it. So in that case, even though geothermal would be very expensive, it's competitive with their option. And so this is so I think that you can't say that because solar is coming or wind is coming and so on, that we can just that geothermal is not competitive. It depends on the situation of the market.
Okay. Another question that I would like to make you is that advances on instrumentation in geophysics are always changing. There are new devices, new technologies. Well, Luis talked us about a joint inversion, which is a good step. But concerning instrumentation techniques, what do you view in near future or mid future in those techniques, these techniques that are applied to geothermal? What would be the new advances? Time lapse, eventually using more the seismic, eventually permanent receptors. Do you see some technological change that can be overseen in the technologies?
There are several methodologies and technologies that are being developed, and I think they might be very promising. And in particular, we're talking about monitoring of geothermal fields dynamically. That means using, like we use NT, that means we just set the instruments, start measuring the natural electromagnetic fields. So we have the seismic noise, which is becoming a very, very conventional strategy to measure. That means you get rid of expecting to have all the natural earthquakes happening all the time. So you have seismic noise measurements, you have electromagnetic noise measurements, and of course all these dynamic methods, I think they are very, very promising for all the geothermal prospects nowadays. Aerial, of course, it is also very, very, very useful, but of course that is limited because of several geothermal areas are very complicated in terms of topography. But still, there should be many developments coming in on those aspects, I would say. At least for geophysical exploration for geothermal targets. Monitoring techniques, I don't know. I'm not very familiar with going into the wells and measuring directly the movement of the fluids in the wells or things like that. But it sounds like very interesting to me. And okay, many, whatever is needed. It's complicated by itself, so very open.
Yeah. Any comment on that, Bill?
Well, I mean, there's an issue of cost effectiveness, and I'm going to bring in another thing, and that is the value per cubic meter of water in the subsurface in a geothermal system at 350 degrees is about 1/80th of the value of a cubic meter of oil so the thing is, that is the best it gets. As the temperature goes down, the value of that water becomes much lower. So that's a number we came up with about a year and a half before the collapse in the price of oil and its subsequent recovery. So all these prices vary, but in fact, the ratio stays about the same for new power contracts as well. So the issue, though, is that we can't, whatever we do to look for geothermal, it has to, for the volume we image, it has to be more efficient than is typically done in oil and gas. And so that's one of the reasons 3D seismic is done in a different way in deep sedimentary systems is because they can't afford, the value of what they're targeting is lower for the volume you're imaging. So you need strategies that are lower cost, and that's true also in at the monitoring stage. So it's not like there's an infinite So the other thing, though, is that there's a very robust, because geothermal is to some extent, as Patricia pointed out, it's in the future. The research opportunities are probably about the same for new geoscience work and so on. There's about the same investment going on by government and universities as there is in terms of the investment in ongoing geophysics in the industry. So when we did the SEG, I helped out with an assessment of worldwide employment of geophysicists, which will be at the meeting in Denver. Will be a panel discussion. But the worldwide employment will be probably higher at universities for new employment will probably be higher at universities and government research institutes than it will be in the industry itself, which is not the case in oil and gas. So that is actually something just to be alert to. And that when you're talking about, for example, these deep sedimentary systems and so on, there are about a dozen of them that are actually productive now and selling to the electricity to the grid. But in terms of worldwide capacity, the expectation is this is tiny. Well, so who's looking into that? Well, people who are doing the assessment, country assessments and so on, are working for, like the USGS has 4 people working on this, for example. I know that this has been, the equivalent, most countries in Europe also have groups working on this. So that's something to be simply an awareness item, and I would think that that would apply throughout Latin America as well. I was just going to mention something that we were talking about in terms of high enthalpy systems, high temperature systems. There's quite a list of countries. So Argentina, Peru, Ecuador, Bolivia, Colombia, El Salvador, Guatemala, Costa Rica, El Salvador, and Mexico all have resources over 250 Celsius. So and those are the ones I've worked on. There might be some I haven't worked on. So I think to say that they're just low temperature they're many of the in a country like Brazil, it's a large country and most of its reserve base would be lower enthalpy systems. And that's kind of eventually the future of geothermal is probably going to be lower enthalpy. But right now, given that, there are geothermal fields running in El Salvador, in Costa Rica, and one under development in Colombia, wells drilled in a couple of wells in Peru, a couple of wells in Ecuador, several wells in Argentina, but no development. Geothermal, Costa Rica has a well-developed geothermal industry, as does El Salvador and Mexico. So there is actually, I was kind of, other than Luis, I was kind of surprised that there was no representatives from the industry. Though I'll have to say, it's the geophysicists I know in Latin America tend not to be members of the SEG in the geothermal business. And I was thinking of calling a few of them up and seeing if I could annoy them about that, but I forgot. So,
well, I think that the web panel have made very important points today. We are reaching close to the time we planned the web panel, the 2 hours. There's been additional questions that we had. We had a lot of questions, and not all has been summarized during this discussion. But many of them has been on technical points, and many of them has pointed to what are the most important parameters in geothermal to be estimated with geophysics, what are the most important techniques. And I think each one of you have commented on that already. So what I would ask to you is to take some time, some minutes each one, to summarize a message you would like to make as a closing remark for this seminar of today. So we can start with Patricia.
Well, I like to say that I'm very optimistic about the geothermal and actually renewable energies markets. I think that although the things may have like a slow start, I think geothermal will pick up. I think the geophysicists, the geologists, they should be prepared for this. I think there will be more push toward clean energies. Like Bill said, he named lots of countries in most of the countries in South America and in Latin America have potential for geothermal energy. Actually, Latin America is a leader in clean energy. So I think we should be very optimistic about this market. I work with Magnetoloric, so I am an optimist, That's why I've been working with this for 50 years. And it's difficult. People think I'm crazy, but that's I think we should look at this market, with care.
Mhm. William or Luis?
Let's see. I think mic's on. I think there's a bunch of questions that were on, like what skills can be easily moved from oil and gas to a geothermal environment. For most geophysicists in oil and gas, the technique that they'll be in some species of reflection seismic or well logging. Well logging, I would argue, is probably the most underused I'm an advocate of doing well logging in geothermal fields. It's a tough sell because the geothermal fields tend to cook the tools, and that's expensive. So but there are high temperature tools, and part of it, there's lots of what would you say? There's a technology limitation there, and trying to make that work over the long term through the ups and downs of the power price cycle has been a challenge. So a company called Tiger tried to direct that at the geothermal business. But if you're in the well logging business, that is something that is underdeveloped in the geothermal business. The issue would be who's going to supply the money for that, and so on. The reflection seismic would be to investigate, is there anybody considering doing deep sedimentary system development where you would conceivably be located? And it tends to be area specific. So all the people in Germany are working on deep carbonates. The people in the Netherlands are working on deep sandstones, and in Australia, deep sandstones. So it's kind of like the oil and gas business. It's very specific. So for that question, yes, there is directly transportable skills, and it depends on where you are and where you want to apply those skills. There's a bunch of people in Germany working in geothermal in these deep carbonates. And so yeah, that's, I see the most. And then the technical questions, I will say, if you go to the IGA website, I mean, you can for free download hundreds of conference papers on things like clay alteration, all the geophysical methods, and so on. Luis we all publish, there's a lot of publications available, and you don't have to pay the journals for them necessarily. The conference publications can tell you the story to get you understanding the context that we've been talking about here. And so there are sources of information available, and I answer emails and help out with education, and particularly advising people if they're planning to go to schools and things like that.
Very well. Luis, please, some comments, final comments.
Yeah. Thank you. After I was having a great time reading all the questions, and I would like to give a final remark from my side. Of course, we are seeing that it's not only a matter of having a push for clean energy in the world, and for us, of course, geothermal is one of our key leaders. But also, if we as earth scientists or specialist explorers, if we go into geothermal, I think that we have most chances of having not the conventional thing that, okay, if I don't work for petroleum industry, then I will move to geothermal or something like that. But rather, if you specialize in geothermal, then you can easily adapt to the other fields. I mean, you can go back to mining, a fossil geothermal system. You can go back to reservoir, which is water, which we already study in geothermal applications. And of course, you can go straight to reservoirs, as we do in geothermal. You can apply all your techniques for geothermal modeling within petroleum industry. So it is rather like geothermal will give you an overall umbrella for a geoscientist, and you can easily adapt to the other subjects. And of course, it's one of the most challenges, I insist, that I have found so far. And thanks.
Okay, great. Well, I would like to thank Luis, Patricia, and William for presenting in this web panel that we have organized as part of the regional committee of the Latin America for the SCG. Also, Mayra for helping us a lot in organizing and setting all things. And well, we are very happy with this panel. I want to tell you that it has a very good impact, a lot of questions. There has been more than 176 participants, which is a very good number for the SCG seminars. And well, thanks again to you and all the participants. We are going to organize in a few months another seminar web panel as well in this format, which is oriented to urban geophysics, geophysics applied to the cities. That's another subject. And also is going to be a seminar, a web panel on geophysics applied to CO2 reduction. That's another one that we are organizing. So, well, thanks to everyone. Keep in contact with the SCG, be member of the SCG and their committees if you are not. And well, thanks a lot. And goodbye and see you.
Just remember, geophysics is multidisciplinary. That's why we can work in many fields, okay?
That's it.
Fantastic. Thank you so much, everyone. And thank you for your time and sharing your experience.
Thanks, Mayra.
Bye.
Thank you.